Hi everyone, my name is Dragos Tatulea, I work for NVIDIA, and welcome to my small tutorial about chasing page pull leaks with Dragons. So let's quickly go over the agenda, the scope of this talk, which is very, very narrow, and the motivation, and then an introduction, thank you, about page pull. We're not going to go super deep, just enough so that we can proceed to the examples. Quick discussion about the toolbox that we're going to use, and then we're going to deep dive. So what is this talk going to be about? It's basically, if we have a page pull leak, you want to know, is this a bug or is this a false positive? And we're going to see what a false positive means. Did anyone encounter this kind of false positives? Yes, okay. I was expecting your hand to be raised, yeah. So in this process, you also want to know where is this issue coming from, so gather additional information. Okay, so the motivation for this talk, I had quite a few of these leaks in our tests, and it was always hard to know, like, is this a driver issue or is this like some kind of application not reading its SKBs from the socket, not consuming the SKBs. And there were also discussions upstream, like, yeah, this can be done, it can be actually, the mail is right there. These are the precise steps, but no one showed it, and I wanted to have this, you know, for other people. I didn't have it at the time, and I figured I could do it, and it's good to have this information in a talk. And I also wanted to learn Dragon, okay, but something else. So quick introduction, what's a page pull? For those who are not familiar, it's a way to allocate pages for receive queues in a fast way and to recycle the pages. There's a lot of information out there. What's important to know is the definition of like the in-flight state of the page is basically once the driver gets a page from the page pull, then it starts to be in flight. Then this page will have some packet data on it. There's going to be an SKB wrapped around some part of this, this fragment, and then it's going to go into the stack. The stack will consume it, and then it will go back to the page pool, and then it's no longer going to be in flight. So a leak, what is a leak? It's basically when you destroy the page pool and you still have in-flight data. That's normal. That's perfectly normal because you can still have application consuming SKBs when you bring down an interface. But if you have it for infinity, let's say a couple of hours, then there's clearly an issue there. So that's a leak, basically. And this leak could be because it's a bug, the driver didn't do its ref counting properly. In the best case scenario, it's a leak. In the worst case, it's actually a double free, so it's like a negative ref count. Or it's a false positive where you have this data is stuck in an SKB which was never read because the application didn't care to read it, or it's reading, maybe it's reading just once a day. And so it's not really a bug, or maybe the socket leaked somehow. So it's just data that is not consumed and it's out there in the system. So we're trying to figure out which one of, so get some information if it's a bug or a false positive. One quick note about the ref count. So we're talking here about the PP ref count. So it's the page pull ref count, not the page itself ref count. So the page pull does take one ref count once the page lands into the page pull from the system. But when the driver allocates the page from the page pull, and after that, the PP ref count is being used. And just a quick mention, so why we can do this kind of debugging, because we have this nice PP magic value, and then we also have direct access to the page pull in there. So this helps a lot with debugging. Okay, so let's discuss a bit more about the page lifetime. As I was saying, you have here the flow. So the driver allocates a page. Okay, it takes this page or a page fragment. It can be both. You know, something will happen in the driver. The driver will post this buffer to hardware. At some point, the hardware will DMA some data into this page fragment, and then there's going to be a completion. At this point, the SKB will going to be wrapped around this fragment. It's going to be marked for recycle. This is how the stack will know to release it to the page pool. Then it's going to be given to the stack. The stack will process it somehow. It will consume the SKB, and then SKB page unref will be called, which will bring it back to the page pool. So this is one scenario where you have a fragment or a whole page, and basically the driver doesn't necessarily have to touch it on the release path. But there's another scenario, which is more complicated, which it can be used and is used in the MLX5 driver, for example, and some other drivers as well, is the bias mechanism, where, okay, so I need to mention something in the previous slide. For the fragment API, you need to know the fragment size in advance. So PagePool has an API that explicitly you can ask for a fragment size and it will give you a page fragment. But if you do not know the size in advance, then another method needs to be used. So this is the bias counter, where the driver allocates a whole page. It splits it into many small fragments, like 64, let's say. It doesn't know if they're going to be used or not. But there's additional complication on the release path because you need a two-step release. The stack releases the SKBs, but then you have leftovers. So the driver has to release its leftover as well. So this is this part here on the bottom. And this can happen in any order. And when you put also the queue teardown in the mix, this can be a source of bugs. Actually, this is where most bugs come from in the driver when it comes to leaks. Okay, so if you look at the broader picture, you have two types of leaks. You have driver-side leaks, either at runtime or at queue teardown, or system-side, which is like this false positive, or maybe a bug. But that's not very likely unless there were some very recent changes that touch this path. Right, so what we're going to do now, we're going to use the drgn debugger with its CLIs. Anyone familiar with the drgn debugger? I think it was mentioned a couple of times. Okay, so it's a super useful tool. It's like a Python-based, it's a programmable debugger. It uses BPF and type introspection. So it's much easier to use than GDB, for example, as you will see. And you can also write scripts. So I developed like 3 scripts that are based on existing ones. Maybe I would like to put them back up there as a separate script that we're going to use here repeatedly in every example. And I'm going to go through them, so I'm not going to talk here. Okay, so let's start. Example number 1. Okay, we have a leak. We see here, so we have one page leak in flight 1, detach time. This tells us that the page pool was detached, so it was destroyed. And okay, we want to find where does it come from. We have one way to do it, is to go to list all the sockets, and then from every socket, take each SKB and check each SKB if it has some data connected to a leaked, if it has a leaked page. So that's super straightforward. In this example, it's just the TCP hash map. So we go through the hash map. You see this is all Python code. You can get the hash map from Dragon. Then you list through the buckets in this second 4. Here we also filter by interface so that we are not, if you have SSH traffic and stuff, this doesn't help at all. And then we go through the receive queue. We can also check the error queue maybe, and list all the SKBs. And then we just take the SKB data or head, whichever, get its page. So this is the Dragon API. And then we can just check, is this a page pool page? This is the PP magic signature thing that I was mentioning. And is this page detached? So we reach into the page pool and check the detach time. And if it's set, we know it's a leak, so we just print this information. And then we do the same for the fragments. So we go through each fragment and do the same check. Just here that we need to basically cast the netref into a page so that we can access this stuff. And you see, this is just Python code that you can just it's like accessing the parts from the SKB in Python is super nice. Okay, then we just move on. Here we have the try catch, because maybe you have some page faults. So, this, you're maybe reading memory that doesn't exist anymore, or it has been overwritten. So this is not like super precise stuff. This is just detective work. Okay, so let's print the page itself. So here you just, with the CLI, you can actually take this. Yeah, I forgot. So the result of this is this output here. It found one page in the SKB in the linear part. Okay, so this is the SKB address, this is the page address. So let's look into them. We have here the page itself. You see nicely you can dump all the information. We have here pp magic, which we just checked, not in hex, so it's a bit harder to see. We have here pp is the page pool pointer itself. And this counter is very important, pp ref count of 1. To me, from the MLX5 side, I know that this is probably not, so the driver has released its side of the page, because if it would have been like a driver bug, this counter would have been much higher. So this is, this is because I know the code around there. And then if you actually look into the page, you can quite quickly see, okay, this, the packet data is in here right at the top. You see here the headspace, the headroom, sorry. And then here, this is actually the MAC address. So this looks like there was a packet here, or there is a packet here. Good, so then we can check the SKB, same thing. Okay, SKB has a lot of information, but the important one is the pp recycle bit is set to 1, so this is as expected. And also here, the head pointer and the data pointer are pointing to the virtual address space of the page that we saw right here. Okay? Good. So this is one way to do it. We go socket, SKB, page. But what if we want to do it in reverse? So you find the page in memory that is leaking. From there, you go and search for its SKB somehow in memory. So let's try to do that. And from there, you can also get the socket, but it's not in this talk right now. Good. So super easy. You just use the Dragon API and you just list all pages and check the ones that are disconnected, the page pool ones. And yeah, we find the same thing. Okay, that's the easy part. So we found the leaking page. We don't have any more information. So how do we find the SKB? Okay, this is again printing the page, same information as before. So how do we find the SKB? Not too complicated. We basically search in the kernel memory for the address. We just need to make sure that we search for the virtual address range of the page. So basically references to the page content. And then, you have 64 bits, right? So you take 12 bits off for the page shift. So you'll only look for 52, but you cannot do like byte-wise search. So you do just 6 bytes. So you search for those 6 bytes in memory, and then you check the rest, and you found the result. And this is what this Python code does. Probably could be done better, where we have here, you get the value, so the virtual address part, and then here you convert it to the proper NDNS, and you get the 6 bytes. This is what I call big needle in this code. And for small needle is when you once you find the result, you compare it against the 52 bits, sorry. So you search this memory. So this is just a snippet of the script, by the way. And then once you have a hit, then you read, instead of 6, you read 8 bytes, making sure that you account for NDNS properly. And then you just read the memory from the value from memory, convert it, and you check the value that it matches the small needle, and that's basically it. So this is very useful. And with this, so we run this, and we found the reference at this address. And the cool stuff with Dragon, it has this identify address method that tells you, it tries to identify where the object is coming from. So it already says, okay, this is coming from SKB head cache, so it's a strong hint that this is an SKB. And then we dump the memory, so we just dump the memory around. The script does this by itself. So basically the result was found here, but I was smart and I dumped like 192 bytes up and 8 bytes down because I kind of knew in this case, but normally you should dump a bit more. But this is a very good hint that, hey, this is the next, this is the prev, or the other way around, I don't remember. This is the callback, this is the head, and this is the data. So this indicates that it could be an SKB here. And if we print it out, we see that it's exactly the same SKB as before, because it's the same example. So just to validate that we get a good result. And then here we have the head address. Okay, so what we found a leaking page. It was in the linear part of the SKB. And I can already tell from the pp-ref count, so we didn't need to do all this dance, that this is it could be a false positive, but I wanted to get more information about where this is coming from. Okay, example number 2, similar but a bit more complex. Let's see, we have one thing. So this is just a simple socket example, just so you know, that was reading bytes, and at some point it just stops reading. And the application doesn't close, it's just there forever. So this is how I got this, this example. So moving on to the next example, we have 2 pages leaking. And what do we find here? We find one SKB using the same script from the beginning. We find, so we list the sockets and then the SKBs to find the leaking pages. We find one SKB with 2 pages. Okay, good. That's what we expected. And then if we look into the skbuff, we see pp recycle is set to 1. Good, that's also what I expected. You see here the pointer to the linear part is probably not, it's for certain not a leaked page, probably not a page pull page. This we can investigate. But then we go and check the shared info, and we check the fragments, and these are the fragments that are leaking. Okay, pretty straightforward. So we went in this direction from socket, SKB, then we went into the fragment list and we found the fragment. But let's try to do it the other way around, where we find the leaking page here, and then we try to find the linear, so the linear part of the SKB, and then we go to the SKB. So we print the pages. So we go through memory, search for the pages. We have 2 hits. We look at this second leaked page here. We print it out just to get some information. Again, pp-ref count 1. Okay, I know that the driver released its side of the page. And right, so now what we do, we try to find, instead of the virtual memory address range, we look for the actual pointer, because the fragment has a pointer. So it's like the struct page pointer that it keeps there. It's not the virtual, it's not some pointer in the address range. So we first search for this, and then we find here we have 2 hits. And this is the cool part. So you see here, you also have output in this dump using identify info that this is a leaked page. Actually had to modify Dragon to print this information, but maybe this can be upstreamed because it's nice. You can just check the memory and you see, there's a page pull here. There's a page from page pull here. It's also leaked. Okay, nice. So we have the 2 fragments here. Here we also have what looks like the length and the offset for both fragments. This could also be the number of fragments. So, okay, this is basically the linear. We know we are in the linear part of the SKB. And what we need to do is to track back to the SKB. So we do a similar search like we did in the example number 1, where we find this address right here or somewhere in the range. That should be in a page as well. We are already in a page somewhere. So we're looking for references to this page. So we do it right here. And we do find it, not just once, a couple of times, so the filtering work is up to you. But we find it here, and once again, this looks similar to the SKB. Here, there's no mention of a page pool, so it's a page coming from somewhere else. And then if we just try to, if you print this SKB, it's the same as in variation 1, so just to validate that we got the same information. And this is the address to the linear part. Right, so this was the most interesting part. From here, okay, we found the leaks in the SKB fragments. The pp-ref count is 1, so it's probably some kind of false positive. We can check which application is triggering this. Yeah. And then the last example that I have is where, so we have a leak. This is based on a bug that I had before. So we have a leak. And then we try to do the same flow. We search for the sockets, and then the SKBs, and then the pages. Nothing is found. Okay. Then we go the other way. We checked for the whole map. We look into the pages. We scan the pages. Okay, we found something. That's good. That would have been worrisome if not. And we peek into so we check the page. And we see here, okay, so pp-ref count 64. To me, as a driver person, I know that using the bias API 64 means that basically the driver never gave off any fragments to the stack. So this is a very, very clear indication of a bug on the driver side. So the driver is leaking this page. And I had another curiosity. So this bug happened only with hardware GRO, and I was trying to figure out, is this in the header page or in the data page? So is the page for the header part or for the data part? And at least in our driver, we don't have them split at the moment. So everything is allocated from the same page pool on the same queue. So I had to abuse this PP mapping pad to use some bits here to mark the header page. And we see here, so I had to modify the driver in this case, so it was not read-only. But I know that this is actually, the bug is in the header part, the releasing of the header pages. All right, so this is what we found. We found that this is a driver bug, and it comes from a header page that is incorrectly released. So ending notes, I wanted to do an example with XDP. I realized I don't have time, and also I couldn't reproduce my old problem, so I had another bug there. But with XDP, in a way, it's easier because I think it's almost always the driver's fault, because the driver has full control over the release cycle as well, if I remember correctly. And yeah, where the examples, I will put them on GitHub somewhere when I push the slides up. And I hope maybe I can get some of this into the Dragon samples as well. And especially the identify address thing is super neat, and I'd like to have this page pool information somehow there as well. All right, so that was that. It was a short palette cleanser. Nothing too complicated for this time of day. Questions? Yes?
So I have a patch series RFC currently out, sticking some more data into the PP magic field in some of the emitter bits.
Yeah.
So one is FYI, and second, if you or anyone else has a reason why this is a bad idea, please chime in. Just like in the 0 bits in the middle of it.
Is it the one with the DMA that tries to track the DMA stuff? I was looking for some, I know the series. I didn't realize, I didn't check it clearly, and then I saw today that it's actually trying to use that. I'm not the right person to comment on that. Maybe Jesper can say. I know that it's many threads, that there was a big discussion, and at some point I kind of stopped following. just waiting to
I
see.
understand. I also just wanted to let you know if, in case you weren't aware, so you
Yeah,
may have to
that
mask off
it
some
might
bits
go
in your
away, right?
flips. Well, no, it will still be there, but you may have to mask up off some bits to do the comparison.
Yeah, yeah. Thank you. All right. Good. Thank you very much.